everyone. Good evening. Welcome to episode number 36 of this Amiga assembly programming series based on the book by Fabio Ciucci, who I thank personally. So let's start from where we left. And you see the book, I don't. So last week we did lesson number 9E2. Okay, so I'm going to remind you what it is about, so that you refresh your memory. Let's go on the Amiga. So this is the example that we did last week, the fish that is like a spring. Just to remind you, we are doing shifting. Yeah. We are doing shifting, and we so far have said that to shift a sprite, a bob, sorry, because that's what, or software sprites as they are called in the modern world. At the time of the Amiga, and I still call them bobs, they were, bobs. We need to add a word in front, a word with empty zeros in front of our bob, which is the fish in this case, so that we can shift it to the right. So I'm just going to leave the fish jumping and see what's next. So actually I will not leave it. I will need to go to the next exercise, which is 9E3. So in 9E3, this time the fish is more intelligent and it's able to scroll from left to right using the blitter. Okay, this scroll is not a hardware scroll, but it's a blitter scroll. We are using the blitter to scroll the bob, to move the bob. Actually, that's what we are doing. We are moving the bob on our screen. Remember, so far we are doing only, okay, to color, one bit plane, what we are using always. I will come to color after this section. As you can see on the book, the next section is colors. So I will be covering that in a minute. I'm going to show it again, because the program exits once it finishes. The shifting, okay, is no different than, in a way, when we are doing a hardware scroll. We shift 16, then we move from 0 to 15, then we move a word, okay, and it's the same, in a way, in inverted commas, same principle. I'm not saying it's the same method, but principle. So let's jump to the book. And let's explain the code for the fish moving. Let's start with explaining the code. So the code here is saying that this is E2. We need to do E3. There you go. So the code is saying we shift to the right, and once done, we shift next 2 bytes. Okay, so we shift one word. It's a very simple code. We move, okay, 0 into the 1, and you will see why in a minute, why we are moving 0 into the 1. It's our horizontal starting position. We start from position 0, of course, so that's why we are moving 0. The next line is 320 minus 32 minus 1. Why? Simple. The width of the screen is 320. The width of our bob is 32 pixels. Remember, the bob has got the character, the fish, and in front of it, it has 16 pixels of zeros in front of it. So in total, that is 32. So because we start from 0, so it's 320 minus 32 minus 1, of course. We wait for our v-blank, I mean raster, which in this case is 255. He is using the old way of waiting for a raster line. I think this was a mistake from his, because actually all the examples that he gives use the new method, but here he's using the old method. It doesn't matter, to be honest, for this example, it's still fine. Then we set the destination address. As you see, we move where we are on the screen into the 0, okay, and there's a reason. Last week we covered this part, it's all in orange, okay, so it's because we want to tell what shift we need, and remember the shift the shift number 0 to 15 goes in here. So what we do is we move where we are. Our shift is 0 currently, okay, where we are, okay. We end it with F, so we make sure that we are only working on the lower 4 bits. We shift the lower 4 bits, whatever the value of our shift is, by 12, okay, so 8 and 4, that is shifting of 12 bits, and that number, when we OR it, is stored in where we have the 9FO. So that's the method that we are using here. I covered this last week, but I'm just refreshing it. So whatever the shift is, let's say it's 1, then there will be 1, 9FO. We know that the 9 is channel A and channel D of the blitter, okay, and FO is our minterm, which I haven't explained, and it will be explained later on. Then we have the calculation of the address for the bit plane, where we are on the bit plane. So we need to calculate which address on the bit plane we are, okay? So depending on the position, we divide by 8. So wherever we are, we divide by 8. So let's say we are in position 100, okay? If we divide that by 8, that means we get 12. 12 times 8 is 96. 100 minus 96 is 4. So we shift 4, and we know that we have to be in the byte, okay, where this calculation gives us, which is 12 words, okay, sorry, 12 my god, 6 words, 12 bytes. That is how he is calculating the address where we need to have our bob, where we need to blit, basically. we add 1 to the corner. Of course, we're adding 1. We need to shift it by 1, no? So we add 1 to D1. So we have our next shift. We have, once we calculate it, we can add it. We wait for the blitter to make sure that it's doing nothing. And now we start our blit. The first one is we are setting blitcon 0 and blitcon 1. And notice it's zeros, okay? And it means we are going to do clear the screen. And because we are not setting any except register D, okay? Here we're setting the modulo, which is of 0, the 66, register 66. We're setting the address of the bit plane that we want to clear, and then we clear it. We're clearing the whole bit plane, okay? The whole of it. So that is why you see the number of lines is 256 and the number of words is 20 per line, okay? After we have cleared the screen, remember the difference between sprites and bobs. There is more to it, but in simple terms is that sprites clear the screen or clear the area where they are when they move, or put back what there was and move. In the case of our bob, we need to clear where it is and then move it. So we clear the screen. Here we are clearing the whole screen, which is not exactly what we want, but for now it does the job. We will cover those things. We make sure that the blitter has finished doing the job. Then again we set the mask, which right now it is always F's, and we will be talking about this later on in the book. Okay, then we do blitcon 0, where we say we are going to use, you remember we calculated the 0 has got this number here, where we say what our shift is and what channels we are using and what our min term is. So we have that, okay? Then once we have that, we can set the value of blitcon 1, which we are not using any special mode for the blitter, so it's always 0. We will cover those later. Then we set the modulo for channel D and channel A. So for channel A, there's no modulo. Remember, this is a move long. So the first 4, okay, are 0. Then the modulo for, remember this is in bytes, okay, then the modulo is 24 hex. Remember we have, which is 36. So here he's showing 40 minus 4 because the width of our fish is 4 bytes, which is 2 words, is 36. So we put 24. This is the address, source address of our fish, so of our image. So that's the pointer of our source, and here we have the address of the destination, okay? Then we do our blit, and our blit is 6 lines high and 2 words, okay? And we continue doing this, going through the loop, D7, okay? So we decremented D7, which is up here. D7 is this value that we initialized with this calculation. We jump up here and we continue with the loop. That's basically it, how we are moving the fish across horizontally, okay? We already saw it vertically, we are doing it horizontally because this is shifting, it's the lesson of shifting. Anyway, let's continue. I believe we've done we've finished shifting, and we are going to start colors. Now, for now, we have limited ourselves to 1-bit plane. Okay, so that means we just had 2 colors. Normally images are more than 2 colors. We know that on the Amiga we are used to seeing more than 1 color or 2 colors on the screen. Normally bit planes follow each other. You know, a bit plane, we have 1 bit plane, then in memory we have the second one and third one and fourth one. We have seen that already. So they are consecutives, and he is showing them here in memory. So this one is 1-bit plane. Okay, here we have another bit plane shown in memory. Okay, and then we have another one. Okay, which continues down here. And notice that a bit plane, okay, starts from the first word. In this case here, the screens are divided in words. Okay, so 16 pixels. So the first word for line 0, and we continue this. When we end, which is when we arrive at word 19, we jump and we start line number 2, or line number 1 as he's calling it here, because we start from line 0. And we continue this till line 256. Once we've done 256, we know that we start the next bit plane, and again follows. Okay, so that is how bit planes are stored in memory, one after the other. Now, what's coming next might frighten you. You're seeing lots of formulas on the screen, but trust me, when you're going to see the code, it's a lot simpler. He is just proving something here, to prove this formula here. Okay, if it was me, I would not have gone through this all this trouble to prove it, but Fabio did. It's not good to know, but in theory you will not really be using that. So what he's saying here is, if we have so let's start from this side. Sorry, we have a bit plane, okay, which is in words. So we know that there are H words horizontally, and then there are a number of lines. So in bytes, okay, that is 2 times H times V. So the number, remember, H is in words, we do times 2, so we get it in bytes, and then times the number of lines that we have. That is how we calculate the size of a bit plane. So if we had a screen of 320 by 256, we have 20 words by 256, or 40 bytes by 256. That's, we have done this several times now. Now, if we have, let's say, bit plane 1, okay, I'm doing this part now. If we have bit plane 1, then the address of this is it means bit plane 1, we're going to call this variable that points to our address of the bit plane 1. So bit plane 2, okay, is whatever the value of bit plane 1 is, whatever the address of bit plane 1 is, plus the formula that we calculated here, okay, which is plus 2 times H times V. So to find the 7th word on bit plane 2, okay, we can do plane 2, okay, we already have this formula for plane 2 plus 2 times 7, of course, because we are on the 7th word, or address 2 plus equals plane 1, because we know the address of plane 1, plus 2 times H times 7, because we know that the height of a bit plane, I mean not the size of a bit plane, plus 2 times 7, or, and this is where address 2 is address 1 plus 2 times h plus 7, which is this formula here. So basically what he's saying, if our image, wherever it starts on the first bit plane, let's say it starts on, as he said, word number 7, okay? If it starts at word number 7 and the address is 100 and our bit plane size is 100 bytes, I'm just going to keep it simple, then we know that the address of the image starts at 200, okay? Given that the address of where our image starts is 100 and the size of a bit plane is 100. So whatever that is, the difference on the screen is always the height, the size of the bit plane. Okay, this is what he's saying here. So you just need to remember that the difference is always the size of the bit plane, which is this formula here, 2 times h plus v. So whatever that position is on the screen. So he then continues and he shows this, okay? If we have an image of 3-bit planes and the image starts here, okay? And you can see that this is the first bit plane where the image is, and it has these 3 lines. Then this address plus the size of the bit plane, the size of this, okay, is this one here, okay? And the same thing plus the size of the bit plane is this one here, okay? So that is what he's saying there. But bit planes are stored till now, okay? Till now, what we covered in the book, okay? Bit planes are stored consecutively, one after the other, on in memory, okay? So far, so good. I just want to see if I skipped anything from the notes of this paragraph, of these 2 paragraphs, just to be sure that I said everything. Okay, so what I didn't mention is that we are always assuming that the screen is this big, because we can have an image, sorry, that the image is this big, okay? We can have an image that is bigger, but we are only displaying this part of it, okay? In that case, some things will change, but for now, just bear with me, okay? So, let's continue. I hope that was not difficult for you guys. So, if we have an image to blit on our screen, first we blit the first bit plane, then the second one, and so on. So what he's saying is, if we need it, and I will give me a second, okay, because there might be somebody that is more intelligent and tell me, you're doing this mistake or that. Just bear with me, I'm following the book. So far, the method that we've seen is that if we have 3-bit planes, and the image is composed of 3-bit planes, then we do a blit of this one, then do a blit of this one, and then do a blit of this one. Okay? That's how we've seen it so far. And Fabio's going to show us how to do this. Please note that this is not how it really happens, okay? But for the sake of understanding, and you need to know, let's say, the basic. It is not, once you understand how we do it here, then you understand what's coming next. So, if we have an image to blit on our screen, this is what this paragraph is saying. First we blit the first bit plane, then the second bit plane, etc, etc, etc. How do we do it? Here he gives a small example code of how this is done. Okay, so this is a typical loop for when we need to blit an image to the screen that is composed of more than 1 bit plane. So First, we do the number of bit planes. We if it's not 3 bit planes, we enter the number of bits. So we initialize a loop. Then we check that the blitter is free. Then we use channel A and D to do the copy, reset the registers, and load the rest of the registers, okay, do the blit, and loop till we have done all the 3-bit planes. Those are the steps in simple terms here. What he's saying here is, as you can see, here we're setting the number of bit planes, we're waiting that the blitter is free, we are setting the channels A and D, okay, we load the blitter and initialize, we load the registers of the blitter basically, and we initialize our blit, okay, line 11, and then we loop. So it's the same thing what I've written here. I just written it in words instead of code so you can understand what's happening exactly. So the values we use to load the blitter, and this is interesting, okay, the values we use to load the blitter are basically always the same for every blit. This is except for the registers, which are the bit plane pointers, the pointers that the source, and source and destination. So everything else remains the same. So when we are looping, okay, we don't really change anything except the source and destination, okay? So we use the formula that we discussed above. That is, when we are looping to go from one bit plane to another, we just add the bit plane size and we blit the next one. By knowing the bit plane address of the first blit, we can add the bit plane size, as I said, to the blitter address pointers and do the next blit for the second bit plane. And remember, the bit plane, the blit plane pointers, we just need to update those, okay? And we use the usual formula to add the 2h times v, which is that is the size of a bit plane, which is what we need to do to go to the next bit plane. So let's go to the examples. So let's jump to the Amiga and do the first example, which is 9F1. So here we have an image. It's a 3-bit plane image, okay? And once I press the right mouse button, okay, the logo where there is Commodore is going to be copied and shifted a bit to the right from the top of the screen to the bottom of the screen, as you saw. Okay, that is what this code does. Now, as you see, it didn't copy one bit plane, but copied more than one bit plane to be able to show what we the full colors that we have. So this is the first routine that we are going to see of how to copy colors. I mean, how to handle colors more than one bit plane on the screen using the blitter. So let's jump back to the book and we go on the examples book. So the example, as I said, copies a rectangular area into another part of the screen. That's what it does. This is the routine. The rest you all know. This is the routine that we need to follow or understand. Here is what we are going to Blit. Basically, here we are loading the source address and destination address. What is this formula, you say? So the 50, okay, is the start address in lines, not start address, sorry, it's the number of lines we need to go down to get where the Commodore logo starts. Okay, we multiply that by 20 so that we multiply that by 20 to know where line 50 starts. Then we need to go shift to the right. I mean, we need to move to the right 64 pixels to get the Commodore logo, okay, text. So we get the 64 divided by 16, and then remember these are words, so we times 2 so that we get the bytes, because we need to specify this in bytes. The destination is the same formula, but we are moving at line 190 where Commodore is. So we are shifting from the top, copying, sorry, from the top to the bottom of the screen. Here we have 3-bit planes, but since we start from 0, we do -1. Here we make sure that the Blitter is available to us and it's not doing anything else. Then we initialize BlitCon 0 and BlitCon 1. I was saying, so BlitCon 0 and BlitCon 1, we are moving, as you see, the normal, our famous number, okay, this one, the 09FO. This is channel A and channel D, and our min-term F0. BlitCon 1 has got 0 in it because we are not using anything. We are setting the masks of channel A all to F, okay? We will, because it's red, as I said, this will be explained later. Here we are setting the pointers, the source and destination pointer for our Blitter to know from where we're copying to this is destination address. And remember, D0 and D2 are the first thing that we calculated here. Okay, so far so good. Then we do the modulo, okay, and the modulo is what we have. I mean, remember, we have is 20 words, okay? So it's 20 words minus 160. The length of the text Commodore is 160 pixels, okay? So it's 20 minus 160 over 16, and that is times 2 because we need that in bytes. And same thing for the destination. After that, we do our blit size. As you can see, we have a height of 20, okay, and we start at position pixel 160 division by 16 so that we know where we are copying it to the screen. So that is how, so here it says 160 is the width of the word Commodore. We have to specify that in words, so division by 16, and that is 10 words. So we're copying 10 words, okay, of a height of 20. Once we've done that, we add the blit plane size. As you can see, this is all the fuss about those formulas that he was showing. It is 40 times 256. Why 40? We have 320 pixels. Division by 8 is 40, you know, and then the height is 256. So that is all what we need to specify to copy it from where it is to the next one in, sorry, that is how much we need to add, okay, for a bit plane, for the next bit plane that we need to calculate. Okay, so we were doing bit plane 1, now we're going to do bit plane 2, but the difference is always the same, is always 40 times 256. We make sure that the blitter, and then we loop. As you can see, once we have looped all the number of times, we make sure that the blitter is free and we return back. So that is all that there is to the to that lesson. Okay, so I believe we have another one that we need to do. Yeah, another 2. So let's do them. So let me show you the Amiga. So first I show you this one so that you understand, you see it better in colors. So here, okay, we are printing text to the screen, okay, using a font, okay. The font is of 1 bit plane, but we are printing on separate bit planes. The reason why I've done this is not the original Fabio, is to highlight the colors to show you which bit plane is which, okay. So the blue is when you are writing color number 1, the yellow is when you are writing color number 2, and the red is when you are writing color number 3. So as you know, color 0 and 1, okay, 0 is the black, 0 and 1 are on the first bit plane, and 2 and 3 are on the second bit plane, or depend on the, actually color number 3 depends on bit plane 1 and bit plane 2. So that is the example. I'm going to show you his original one, and I'm going to leave his original one because the code covers that. So he has done something similar, but the colors are not so evident. So that's why I created that contrast. I'm going to leave the Amiga and switch to the book. And this time you will see that he's saying writing characters using the blitter. Okay, so before I explain the routine, okay, it's actually 2 routines. I just want to show you something. So this is what we have on the screen, and you can see we have this text and this text. Okay, notice that first line of first bit plane, okay, there is the text, but there's nothing in first line of the second one. Okay, then there is nothing in the first one, but there is something in the second line of the second bit plane. Now third and fourth has got something, third and fourth line, and same on the second bit plane, and this continues like this. So if we take the S is common to both, but the E is not. Okay, this is to show the colors. So where in this case this is color index 1, in this case this is color index 2, and when they are both the same, okay, this and this, that is color index number 3. The rest is black, where it's empty is black, is color index 0. So we have not two routines, one routine, but the initialization is twice. Okay, why twice? Is one for each bit plane. So first we do the first bit plane, so we get the source address where our text is that we want to write on the first bit plane, and then we get the source address of the actual destination address of bit plane 1. Then we do our routine to write text to the screen. Once we've finished writing text to the screen, we get our second text, we get the pointer to the destination. So this is source, this is destination. Okay, this is the pointer that goes to the second bit plane, and then we call the same routine. How is this magic done? This Tampa, okay, how he's printing characters to the screen is very easy. We know, first of all, each character is 16 pixels by 20 pixels high. Okay, so 16 times 20. Here, okay, we are moving the number of lines, so y, okay, y-axis, the number of lines that this, how many times this character can be printed on the screen. Okay, how many lines can we have of this character that is high 20 pixels? Okay, it fits 10 times. Okay, so we are, and if we do 10 times 20, that is 200. Okay, our screen is by 256, but Fabio decided that we only need 10 lines on the screen. That's why the bottom part of the screen is not used. So that is how many, that is the y. This is the x. How many words do we have horizontally? And that is 320 pixels, so that is 20 words. So to print the character, okay, first we clear the 2. Okay, that's understood. Then we are going to move in the 2, okay, the value that we have in 80, which is, remember, 80 points. In this case, if we are in this part, to where the text is. So 80 points to the first letter that we want to print to the screen. Since the letter is in ASCII, okay, we need, and our font starts from letter number 32, we subtract 32 from it to get the first letter. We add that value times 2, so an addition of a number by the same number is actually doing an addition of 2. So here he avoided multiply, MUL, MULU, okay, he avoided the MULU instruction on the 68,000 because an add is faster than the multiplication in this case. So 10 plus 10 is 20, but you can do also 10 times 2 and it's still 20. So that's what he did there. We move that value into address A2, okay, and then we add the font base where the font starts, okay, and like that we know which character the start address of the character that we want to print. We test that the blitter is not doing anything as always, and then we start the initialization of the blitter. So as always, we are setting blitcon 0 and blitcon 1, in this case with registers with channels A and D, and the min term of f0. The mask for channel A is all f's. Then we set the source and destination address of the character that we want to print, and the destination is, of course, the bit plane, the position where we are going to print on the bit plane, which we calculated. As you can see, A2 is here, and destination is, we passed it, the bit plane address is A3. Here we specify the modulo. Now the font, okay, is 120 bytes. 120 bytes, okay, but the font width is 2 bytes, so 120 minus 2. So that's why he has a modulo of 120 minus 2. The screen, the destination, which is the screen, is 40. Of course, it's 212 pixels, so 40 minus 2, which is the width of what we have here. Okay, and then we do our blit. The blit, as you can see, is 1 word and 20 lines high. Now the difference, he introduced something new here, which I'm explaining. He's saying 6 bits are shifted to the left. This is the same as doing 20 times 64. Okay, so we are shifting it 6 bits, is the same thing. Sometimes people write this, sometimes people write this, so he's making you get accustomed to it. I avoid this as much as possible, but sometimes I cannot, so it depends. The reason why I avoid this is because when you look at the code, this is much more visible to me what it's doing. However, sometimes the shifting makes more sense. So in this case, I prefer 20 times 64 because I know the 64 is fixed and I know that the 20 is the height. Of course, the next character that we need to print on the screen is 2 bytes ahead from where we are. So we add 2 to A3 to print the next one, and we continue printing, okay, till we arrive at the end of the line. Once we arrive at the end of the line, so the loop finishes, we jump here, and this one calculates how much we need to jump to print the next character, and that is always, in this case, 40, which is the width, okay, times 19. 19 is because we start from 0, so 40 times 19. Remember, the 40 is 312 pixels division by 8. And we start again. We do the horizontal position, we increment, and do the next line. And it continues this for 10 times. So we do first the X, and then increment Y, then the X again, increment Y, and it continues like this. It's the normal for next loops in BASIC. And we have done this example. If there was something I didn't explain, I would stop, but I explained it all. So let's do 9F3 and jump to the Amiga. And this time we have the pattern, which is composed of 2 bit planes, and it's being drawn to the screen and filling up the screen. Now this pattern, okay, the difference between this one, this example, and the previous is that we were splitting the characters one after the other on the same bit plane. Then when we finish the first bit plane, we jump to the second one, and we did the second bit plane, all the characters for the second bit plane. In this case, we are doing the blit on the first blit plane. Once we finish, we jump to on the second blit plane and we do the blit there. Then we come back to blit plane 1 and we do that again. We do a blit on blit plane 1 and then on blit plane 2, and we continue like this. It is slow not because the Amiga will take so much time to print it on the screen. It is slow because Fabio introduced a loop to show you a delay using the raster, weight raster, okay, to show you what is happening, to show you so that you can see it being drawn on the screen one by one next to each other, and also it's an, in a way, nice effect. So let's jump to the book and explain that. So we're going to blit to the screen an image that is 16 by 15 pixels, okay? So X is 16 pixels, Y is 15 pixels, but we skip one line. So in total we have 320 by 256. This is the routine that I'm going to explain, and I did this line to divide the code and make it a bit more visible, because it was not so visible to the eyes. So the routine filmem requires 4 things. I know you're seeing 3, but it's also this one below, okay? The routine requires where the start address of bit plane 1, the start address of bit plane 2, the start address of the image bit plane 1, and the start address of bit plane 2 for the image. So that's why 4. So we are using A0, A1, A3, A4. We're skipping A2. Once we initialize those registers, we wait for the blitter to finish if it's being used. Then we set the channel for channel A, the mask for channel A, Fs. This will be explained later, okay? We set the modulo, okay, for channel A and channel D, 1 to 0 and 1 to 38. 0 is because the image, the source, doesn't have anything to skip, so it's 0. And on the screen we have 40 bytes, but what we are blitting is 2 bytes, 1 word, so we put 38. Here we're setting blitcon 1 and blitcon 0. Blitcon 1 is 0 for now. As I said, we're only using the area mode of the Amiga. And the blitcon 0 is 09F4, which is, as you know, 9 is channel A and channel D, and F4 is our min term, which will be explained later what min terms are, but for now accept F0. We've done all that setting. Now we're going to tell it, hey, there are 16 lines, so this is the Y. 16 times we can print that image to the screen, okay, in the Y. And there are 20 times that we can print that image to the screen horizontally. Remember, we're doing -1 because we start from 0. Here, we are waiting for, this is the routine that he should have been using in the first place since we've done chapter 8, but for some reason he didn't do in the previous examples, and we are waiting for raster line 264. Okay. So once we wait for raster line 264, and this is how he introduced the loop so that you can see it being drawn on the screen, okay, we start setting the blitter. So we set the source and destination pointers, which we know they are in 80 and A3, okay, and we do our blit size, which is the height is 15 and the width is 1 word. So we do our blit, we wait for the blitter to finish, we move sorry, I'm just checking something. What was BlittCon? Okay, so yeah, I just thought I made a mistake and I was going to correct myself, but I said it correctly. So that was the first bit plane. Once we finish the first bit plane, we do the second bit plane after we make sure that the blitter has finished blitting. So we set the source and destination again of the bit plane, and there's nothing else to set. So we do our blit, which is again 15 pixels high and one word width, and we wait for the blitter to finish. Okay, then we have done bitplane 1 and bitplane 2 for the first image on the screen. The first one in the top left hand corner. The next one is 2 bytes ahead, so we're at 2. Okay, on the so we put it on the screen, and remember this is horizontally, and we also need to add, so that is for source, for destination, bitplane 1, and this is for bitplane 2, so we also need to add 16, okay, which is 2 bytes. So bitplane 1 and bitplane 2, we added 2 to them, okay, for the destination, and we loop, okay, and like that we do the first row of the screen. Once we have done the first row, which is the 20, we set that there are 20 of it in a row. We have finished, we jump here and we calculate where we need to be next on the bit plane, okay, which is the height, okay, the height of the image times 40, okay, and we do this for bitplane 1 and bitplane 2 again, and again we loop again and we do a line, and we continue doing this one after the other. So that is the example that you just saw filling the screen. This is the image that we are blitting. And we arrived to lesson 91. Now, we need to go back to the book, I believe. So, now we arrive to a part that I will not be able to finish. There's not enough time. However, we will start it. I will revise it again next week, because this is where the miracle happens. So far, I said that when we have more than 2 colors, okay, so more than 1 bit plane, okay, we were looping and going through each bit plane and copying the image for each bit plane and moving it, no, or whatever we need to do. Now, that is a lot of work for the CPU. You know, we have, every time we're setting the blitter will always take the same amount of time. No, if it's doing, I don't know, 30 words, and each time we divide those 30 10, okay, so we do it 10 10 10, okay, let's say we have 3 bit planes, okay, the blitter to blit those 10 or blitting 30 together will always take the same amount of time. But the CPU, okay, is wasting time doing that, because every time we are using the CPU to set all these things and looping also for each bit plane. So the magic is, and I can tell you now, we can do this with just 1 blit. But the image needs to be stored a bit differently, and this is when we have arrived to the part where the image is saved or used, having an image that is interleaved. an interleaved bitmap, okay, which I'm trying to highlight, but the Acrobat is not letting me, but it's this word that I am indicating here with the mouse. Okay, so I will explain, there are two things to this, okay? I will explain how to create an interleaved bitmap. That will come later on. For now, I'm going to explain what is an interleaved bitmap. So far we have always said that the bit planes come one after each other. So we have bit plane 1, once we finish we have the second bit plane and then the third bit plane. I mean normally, okay, I'm not saying it's a rule, but normally they are consecutive. However, imagine, actually not imagine, this is what really happens. Imagine if we have, let's say, line 0 of bit plane 1, line 0 of bit plane 2, line 0 of bit plane 3, etc, etc. So the image is stored or is grouped, instead of by bit planes, is grouped by lines. Okay, so if we have a 3-bit plane, there will be line 0 for bit plane 1, line 0 for bit plane 2, line 0 for bit plane 3, then line 1 for bit plane 0, bit plane 1, then line 1 for bit plane 2, and line 1 from bit plane 3. I mean, I'm even repeating it, I'm getting lost. But that is what interleaved bitmap is, and I'm going to show you what Fabio drew. Okay, so he's showing a bit plane, the first line of bit plane 1, then the first line of bit plane 2, and remember they are, and see, notice they are consecutive. So if bit plane 1 finishes at word 19, then word 20 is where bit plane 2 starts for line 0. Here I'm showing I'm showing this instead of the first one because it's divided on the book, but line 1 for bit plane 1, line 1 for bit plane 2, no matter how many bit planes we have, then let's say we have 8 bit planes, line 1 for the 8-bit plane. Okay, it's how this is, and this continues one after the other. That is what an interleaved bit plane is. Now we have seen raw, we have always saved an image as raw, and I've showed you how to do that using the IFF, not the reference one, not the IFF converter, but IFF to AGA, okay, converter, which I will show you next week again how to create this. But because we are I'm working on a system that is using Kickstart 3.0 and above, okay, reference converter tends to, let's say, be a bit funny how it works. So I prefer, and also the IFF to AGA converter requires a higher kickstart. So I will be showing you that. So let's see how this can be done, and forget the blitter, okay? Just think about bit planes. For this to happen, this requires two changes, okay? The first one is the way we calculate bit plane addresses, because remember before we are saying that a bit plane, the next bit plane bit plane 2 starts after bit plane 1, which is the size, so the offset to it from the base address of bit plane 1 is the size of a bit plane. This one, in this case, is the size of a line, but given that we have 2 bit planes. Okay, so I will correct myself in a minute, because it's not exactly correct what I said. So this requires 2 changes to the way we display bit planes. The first one is the way we calculate bit plane addresses. We are calculating the next bit plane in width, in bytes, number of lines. So let's say we have a 320 by 256, and we divide this by so that means that we have 40 bytes by 256. Okay, that would have been the next bit plane, but with interleave, okay, line 0 of the first bit plane will line 0 of the first bit plane is that doesn't change, it's the same address. Okay, so that is the same, but line 0 of the second bit plane, so remember they go one after the other, is the address of the second bit plane. So if I go back to this diagram, okay, this is the address for the first bit plane, which doesn't change because it will be always that where it is, but the second bit plane will have that address. If we had bit plane 3, then somewhere here we will have the address for bit plane 3. So the pointer where the bit plane starts is that, okay, line 0 of the bit plane, where line 0 of the bit plane starts. That's the first thing. So this means he's going to use the y variable. This means that between y and y1 there are the lines of the other bit planes. So if we are on line 0 and then we jump to line 1, and of course line 1 is all the I'm talking line 1s of a group of bit planes. Okay, what he's saying here is that between line y and line y plus 1 there are all the lines related to all the bit planes. And as I said, each line points is the between line 0 and line 1 is the address of each bit plane. Now let's explain the second change, which is the modulo. Okay, and I have all this paragraph is this line basically. Okay, so nothing to be afraid of. So if we have 3 bit planes, okay, the modulo, okay, we know that the modulo is how much we need to jump. Okay, so the modulo is calculated the number of bit planes minus 1, of course, times the number of bytes per line. So why is that? So if we have 3 bit planes, okay, the first line is for bit plane 1, but then line 1, okay, that was line 0. If line 1 starts, okay, after we jump the lines related to bit plane 2 and bit plane 3. So if each line is 40, that means we need to jump 80, because we have 3 bit planes, and as the formula says is number of bit planes minus 1, so it's 2 times number of bytes per line, which is 40 per line, so it's the number is 80. That's all what he's really saying there. It's not, once you get this, okay, it's nothing that you need to understand. Of course, in the code that we will have to do next week, because this is where I finished yesterday, I made a note. Thank you very much, guys. See you next week, and I hope you enjoyed my stream. See you. Bye bye.